Okay, so thanks. All right, let's talk about today's lecture.
Blaine, before we get into that,
Yeah,
I just want to ask, did you get my email from last night?
I did. And so actually, thanks for reminding me. I have a small update on that. I still have to contact the people at the plant and kind of talk with them a little bit. But my understanding is on Tuesdays, so April 5th, I guess, is a no-go because that's actually Easter Monday. Didn't realize that. So the main option is April 6th, which is the Tuesday, and I talked to Mary France Jones. My understanding is on the Tuesday mornings, you guys normally have a lab, but there is no lab scheduled for that day. So I'm hoping that some people will be available since there's no lab in that time slot. If that's not the case with you, I still got to talk to her because I realize not everyone is necessarily in her class. But what I'll do once I talk to the plant is make up a schedule and divide everyone into the two groups, and we can always do some swapping if something doesn't work in the end. Lots of time to think about it anyway. The other note I was going to say, I think I mentioned I was going to tell you when test 4 was. I haven't decided that yet, other than it won't be next week. It'll probably be the following week. Just got to see where we get. I think test 4 is usually topics 6 to 9. So I have to look into that, but I will guarantee you it's not next week. So it just gives you a little bit more time. So we finished off, we're almost done topic 6. There were just maybe 2 or 3 small things to talk about. One thing that of course is important for municipalities is fire hydrants. And we talked a little bit about the need for having the right amount of water and pressure to of course extinguish fires. And probably most people don't exactly know what's going on with a fire hydrant, but basically it's connected to the water main and there's some sort of valve, and you can see that's what's going on there. So obviously an important part of the system. Here's a little cutout. It's a little model and kind of shows the same thing. And you can see the valve there. And sometimes they're found flushing these. There was one I saw being flushed last year on, I think it was Pond Crescent. I was going for a walk and they had it basically wide open. There's a massive puddle there. So I don't know exactly what's going on, but sometimes they do flush them. Probably had something to do with the flooding. Maybe water got into the mains or something like that. So here's what these service connectors look like. And so sometimes people have them in their yards and in convenient places. Poor David Smith has one in the middle of his driveway. I feel bad for him. At least it's not high enough that it's like hitting the car or anything. And you know, you can drive over it, but you know, he says he stubbed his toe on it more than once. That's not very fun. But when I was growing up, I had a friend who had one right in his front yard, and it was basically knee level. It was sticking out really far. And I remember how many times we were running around his house, and you know, I definitely ran into it at least once. No fun. Not much I'm going to say about valves. So this is kind of a summary of the last topic. Really is that, you know, we are trying to get water from a source. There's going to be, I guess it doesn't show the treatment plant in there. There's going to be a treatment plant somewhere in the middle. Sometimes water stored, distributed to different homes. And there's kind of the list of the last topic. So we're going to be talking about these will be the next few units. We're going to talk about water treatment and a few other things around that. And so not quite the next unit yet, but we're getting there anyway. Okay, so first, before we talk about water treatment, I want to talk a little bit about pollution and some of these quality standards. So you're introduced to them a little bit in Lab 3. Lab 3, you may remember, you were asked to take a look at what's that document called, the document for guidelines for Canadian drinking water. And if you look in that document, it actually gives the exact standards that are expected of drinking water. So for example, how many parts per million of arsenic is acceptable, or how many parts per million of copper. And it's a big long list, and that's one of the things we're going to talk about a little bit here today. So first, let's talk a little bit about pollution. So here's a fill in the blank question. Water is a great solvent because, and remember what makes water a great solvent? We're looking for a chemistry word.
Polarity.
Yeah, somebody said it. I heard somebody say something about polarity. Yes, because it's polar. So water is a very polar molecule, so it can interact with a lot of things very well, particularly anything else that is polar or charged. And so you can see in this diagram, it's showing water interacting with sodium chloride, both ions, and able to dissolve it. And you can actually dissolve salt in a pretty high concentration of water because of these water ion interactions. So here's another question. Does pure water exist?
If you think, are you talking about the like non-salt water?
Sure. Like if you were to buy, let's say, distilled water from a hardware store.
That would actually be true because Canada is known for having the most percentage of the freshest, purest water in the world.
So it is a bit of a trick question. The answer is actually no, although it just really depends on what you mean by pure water.
Fresh mountain lake water.
Fresh water is not pure water, right? So if you think about some of these labs we've tested for, what have we tested for? Calcium and iron. One of the tests that you guys did in some of the labs were a snow melt, right? Which you think would be really pure, but there was at least something. So most water does pick up something as it goes along, a little bit of calcium, iron and whatnot.
I actually, that is actually something. Okay, so this is speaking of water, because as you know, water is the gas, solid, liquid, and as you know, when it's solid, it's ice, right?
Yeah.
It's actually so this was something that I remember. Maybe Fahad will remember this too because he was in Neil O'Donnell's class last year. But the glaciers from long ago.
Mm-hmm.
So as you know, I'm sure as you heard aware, so like many eons ago, like the Earth's climate was different a couple times.
Okay.
But some of the glaciers, so like some melted, they had like I forget the the ion, but it was like pure like ion.
Well, sure. Yeah. I mean, when they do those ice
It was,
cores,
from like a long time ago.
yeah, when they do those ice cores, they can take a look and see, and learn all sorts of information about the conditions during certain times. And one of them, of course, we'll talk about a little bit is trapped gases, such as carbon dioxide and whatnot, which can tell you a little bit about the CO2 levels in the atmosphere. But that's kind of, one of my other points is that even if water is distilled water, that we can make distilled water in a lab. We can make it really pure. It's never usually 100% pure because at least at a minimum, it will have some dissolved oxygen in it as well. There are some artificial ways to make it, but it's really hard to keep it pure because, of course, as soon as you expose it to the atmosphere, carbon dioxide and oxygen can get into it. So it's very hard to have exactly pure water. We can get pretty close though.
Mm-hmm. Blaine, did you know that, I don't know if this is a myth, but do you think that water can conduct electricity that by itself? Because actually water itself doesn't conduct electricity. It's what's dissolved or something in the water. The water by itself isn't conducting.
It's usually dissolved ions. The more dissolved ions you have in there, the better it conducts. Whether pure water can or not, I'm not sure. Probably not very well because you're right, it needs the ions in there to conduct the electricity.
Yeah, so you're thinking like the oceans, like it's the stuff in the oceans.
Yeah.
It's so naturally the ground is it's like they become attracted to each other. That's why you hear of lightning strikes. But a lot of times too, it's if it's not on land, lightning strikes the ocean.
Right. So let's talk a little bit about pollution, and I want to talk about types of pollution here. So pollution is one of those things that I think most people they know what it means. It means that there's something in the water that's making it dirty, right? But here's something a little bit more precise, right? polluted means the water is not good enough for that particular use. So think about water. We don't just drink water. Think about all the potential uses of water. We could water our lawn with all sorts of things. You know, I know some people that, you know, anytime they have water, let's say they boiled potatoes or vegetables, they use that water to water their plants. The plants are totally fine with that, right? Sometimes we want a little bit cleaner for drinking or other things. So usually we're just
not all plants should be watered with tap water though. So like we have a plant. My mom has a plant here, and when she waters it, like it's a brush of it's like bottled water.
Yeah.
Because even the tap water, like with different things, but because people put different things in their tap water.
Well, and
like,
some plants are going to be a lot more tolerant to, you know, different ions and whatnot.
But yeah, I remember. But yeah, I know. My hometown, I had an example of river pollution. There was Montague. So there was a fish plant up at like one of the pipe, if it was clear, it was blue. But on the bad days, I've seen the Montague River, like it float the sea, but it was like a murky green color.
Ooh, yeah, of course. I mean, there's lots of things that can be dissolved in water. So I want to talk about some classifications of pollution here in a moment. But
I think that counts as a form of pollution because it was
well, for sure, it's putting something in the water, and it's of concern, right? If you know, we don't want our water to be green in color, particularly for drinking or anything else. Usually there's the implication that pollution is a human caused thing, but that's not necessarily the case, right? You can imagine there's all sorts of things that happen naturally that may make the water unfit for a particular use, right?
Yeah, we actually, okay, another thing, it's a little bit, but then I'll let you back to this one, there's something. So, my hometown, so they had built a new high school, but the old one got destroyed, but it left lots of scrap metal, and they left it sitting there for so long. So, and PEI sometimes knows get a lot of rain.
Yeah.
And you know how the chemicals sometimes, like when you leave scrap metal like that around, can corrode? It literally, there was one day this happened, and all the corroded material floated out like liquefied, and it went all the way down in the hill, and it actually surged straight towards it, right in towards the Montague River. And then there was like, and then like all the rats came flew around the city and went right down the street, a whole horde of them.
Oh, no fun. Oh, yeah. I mean, there's lots of
from a rain that happened in a rainstorm.
Yeah, I mean, lots of things like that. So I want to, like I said, classify pollution a little bit here. So here's some things, you know, and you mentioned a couple of these things. There's a whole bunch of, I have actually a chart we're going to make here in a moment. So you guys may want a piece of paper. But here's some examples of things that probably most people are thinking of pollution. So you mentioned the corrosion, or the, I think you said it was a fish plant. All sorts of industry, of course, you know, at least traditionally, they would sit by a river and dump whatever into the river. Now they can't usually do that anymore, thankfully. But anytime there is an industry near a water body, there's always concerns, of course, about some sort of pollution or leaching or whatever. So one way to classify pollution is whether it's a point source or dispersed source. So probably pretty obvious what that means. A point source basically means all the pollution is from one place. So that could be a pipe, let's say, or somebody's dumping something directly. Dispersed sources means spread over an area. Kind of a typical example of that is agriculture, or you know, anytime there's roads. Of course, in Canada, in many places in Canada, we put road salt. So that road salt, of course, is leaching in many cases into swamps and rivers and things like that as well, which can be a problem, right? Depending on how much we use. Don't use as much salt up here in Fort McMurray. I guess it's too cold for that, which is kind of nice. I know some places I've lived, they're a little excessive with the salt, and it just gets on everything. It's pretty bad.
The salt?
Oh, yeah, yeah. Like when I lived in Southern Ontario, pretty much everybody I knew was buying some sort of rust protection for the vehicle because the vehicles just would rust right out within a few years if you didn't do that.
Oh yeah, like oh yeah, it's like yeah. Oh yeah, I know, because like all that salty, all that because the Great Lakes, they have all that salt, right?
Yeah.
Yeah.
So what I wanted to do was talk a little bit about, this is a way to classify pollutants. So usually I do this on the board and make a little table. What I'm going to do instead is a little neater than my handwriting, as I'm just going to type this up into a Word document and talk a little bit about these different types of pollutants. So what I've done, you can see I've got the types on the left there. There's nine types. And I want to talk about where we might get some of these type of pollutants, examples. And of course, the other important thing is what is the effects from these kind of pollutants, right? So oxygen demanding wastes. These usually mean things that are going to decompose and they're going to consume the bacteria during the decomposition is going to be, of course, consuming that oxygen. So a classic example of that is sewage. But there's also wastewater from various industries. So wastewater from things like food processing. I'm thinking of canning industries or slaughterhouses. So all those things, of course, have organics in them, and those organics, like I said, as they get consumed by aerobic bacteria, they're going to consume oxygen. Another big one is pulp and paper mills. I don't know a ton about the pulp and paper industry, but I imagine there's probably lots of organic products. They take the bark off the trees as part of the process, and all that is waste that if it gets into the water, it's going to, of course, reduce dissolved oxygen. So that's the effect, right? Yeah, so this all reduces dissolved oxygen. And that can kill aquatic life. All right, so that's the first one. I'm not exactly sure why. You can see I have a second one. Actually, never mind, I do know why. Let me look down here. So another way you can think of this is oxygen demanding waste. Now we'll just call this as, I'm going to put this in quote, regular organics. So meaning organic waste, but not the toxic kind. So you can see number 2 is toxic organics. So what do I mean by toxic organics? I mean things that are chemicals that can, harm wildlife in, as toxins, right? So they literally can kill wildlife. So a good example, of course, is certain type of pesticides. So DDT is a good one. We can include some pharmaceuticals in there. And a few other things too are just really nasty for the environment. So things like paints and solvents and other chemicals like that, right? So what type of effects? Toxic and adverse health effects. And this is, obviously to the wildlife because they're in the river, but also can affect humans as well, right? The sad thing is we banned DDT. I don't even know when DDT was banned, a long time ago. And the studies
1972.
Yeah, and here's the scary thing is that I'm assuming all of us were born after 1972, and probably all of us actually have DDT in our system. That's how long it's been around. So kind of scary.
DDT,
oil,
toxic.
Oil of, hopefully that one is obvious what it means. We're talking about
Blaine, did you mean DDT, not DTT?
Oh yeah, okay, there we go. Thank you. Petroleum, bitumen, those kind of things. Another group called polyaromatic hydrocarbons. I'm going to talk about those, or polycyclic aromatic hydrocarbons.
When I think of oils, isn't there some natural oils in the water too, Blaine?
Oh, of course there is, yeah, and that can be considered pollution or natural. And in huge cases, a lot of the natural, when these things naturally end up in the water, usually it's not in huge concentrations.
Yeah, because I was just thinking about that because it was something I learned from here because it's actually so our oil is like naturally old oil because of the remnants of a lake and why they find seashells and stuff like that to this day.
Well, of course, and like I've seen it. If you go down by waterways, and there's the boat landing, and I think there's a dog walking park. I don't know if you guys know that area, but there's a little area if you go along there. There's actually a beach. So I've been there a couple of times and gone swimming. Haven't gone there since they've done all that construction in there, but it's a relatively nice beach, soft sand, and the water is decently clear there. But there are places when you stick your foot into the sand, you see actually oil come out, and there's a lot of places along the river like that, of course. So pollution in small quantities, right, is not so bad. You guys know the saying about pollution? Dilution is the solution to pollution. Do you know that one?
Yeah.
So
no, I never heard about that one.
Diluted pollution is not as bad as concentrated pollution, right? But anyway, it's just sort of a funny saying, but it's kind of true in some ways. So pathogens, pathogens are coming from mostly sewage and some from agriculture. So you can see that, you know, sewage is obviously up here number one, but the biggest concern about pathogens, of course, is illness, right? So you could have cow manure that is consuming dissolved oxygen, or we could have cow manure that's maybe giving us cryptosporidium parasite. So those are two different effects. So it's usually classified as different. Nutrients. So nutrients, we were talking about algal blooms. So fertilizers is one, and of course natural fertilizers, which is of course manure, so agricultural runoff. And so this is directly related to algal blooms. So stimulate algal blooms. And in some cases, various weeds as well can be a concern.
And it'll decrease the dissolved oxygen.
Reduce dissolved oxygen.
Hey Blaine.
Mm-hmm.
Doesn't our local Groundwater Lake have like algal blooms or?
Yeah, it can some summers. Yeah, I think I was mentioning in class a couple of weeks ago that there's at least one summer. I think it was the summer before the evacuation that it was particularly bad, and I remember trying to go.
I actually remember. I was
practically
Lake. I took us. It was. I actually took us. That was the first time I took a swim in Groundwater Lake.
Yeah, it depends on the year. It's a relatively fertilized lake. So there's lots of nutrients in it. You get the right year with the right temperatures and sunlight, and you can get algal blooms. There's always a little bit of it in there on that lake. Some years it's not so bad, and then other years.
And I think when I think of algal blooms, I think oxygen takes a part in that as well, or like that's what I think. But
it's mostly things that stimulate the algae, right? So you're talking about excess nutrients, a little bit extra sun and light. And the algae itself, when it dies, the decay process consumes dissolved oxygen.
And could it also be that the water, like, it doesn't really flow much anywhere else?
Yeah, sometimes the flow, particularly when you have still water, it gives a chance for the algae to establish itself. Yeah, for sure. So number 6 is soil and sediments. A big one there is that's affecting water turbidity. So that's actually what's going on with the Athabasca. In the spring in particular, is that the water, it looks really nice from a distance, but you probably notice in the spring, if you go for a walk along the Athabasca, it's looking pretty murky, and that's not good for drinking. So we have to get rid of the extra clay and all that. Soil and sediments can also affect fish. They're trying to breathe with their gills, and that's obviously not something they want to have in there. So they might hide during those seasons. So inorganics.
We had a lot. Yeah, I was just saying because that's probably when we mentioned the stuff that was in Athabasca in the spring. That's probably why we had all that boil water advisory when it flooded into the drinking water.
Well, and part of the thing is there's so much in there. They as I mentioned that in the spring, they just weren't sure what was in every water line. So that is a big precaution, right? Until they have every system tested and all that, right?
Yeah, I remember when we were running the bath, the bath water was just murky.
Oh, for sure. And I remember, I don't know what year it was, not this past year, but there was one year they were doing some work in the pipes, and there was extra iron in the water. And so we definitely saw a little bit of a color to it. And
there was
but the city,
then there was 2016.
Color change.
yeah. And sometimes the city says, oh, don't worry about the color. And other times they say it's a boil water advisory, right? So by inorganics, we mean heavy metals. So there's a little bit of a review of the periodic table. Maybe you know some of them. Hg, anyone know what that one is?
Mercury.
Mercury, Cd,
Okay.
Cadmium.
cadmium, Pb,
Lead.
lead, As.
Arsenic.
Yeah, and
Copper.
that's right. Yeah. So those are some of the ones that we think about. And again, that can be from industrial processes. Sometimes you get them from just natural in the soil. And so one thing about these is that they're non-biodegradable with that. And they're persistent, meaning they don't go away. And this can lead to health effects. And again, health effects.
And this can lead to water tasting metallic or salty.
Yeah. Usually though, when you get that, it's not the heavy metals. These are actually some of them, like mercury is relatively toxic, even in small amounts that you're not going to taste it necessarily. But there's a high enough there to give a health effect. So the next one is heat. So this is excess heat from thermal power plants, for example. So my hometown has an electrical plant, and so it uses water as a coolant. And so this time of year, you can drive along the highway and you eventually come along the power plant, and everything is, just like Fort McMurray, it's all frozen and snowy, except for this one little lake that's kind of just across the street or on the other side of the highway from the power plant. But you're not necessarily allowed to do this so much nowadays because, of course, that kills the wildlife. But when they had built the plant, this was part of the permit, and so they're still allowed to do it. But they were able to discharge the water in there, and so it's basically a thawed lake all year round. I don't think anything lives in it because the water is too warm. But sometimes these things happen, and so this is actually a criteria of like our wastewater treatment plant. We're not allowed to discharge water that's too warm into the river, or else it's going to affect the wildlife. So this will do a few things like increase bacterial growth. Again, it all depends on exactly how much heat we're talking about, and decreased dissolved oxygen. Remember, that's the correlation. The warmer the water is, the less oxygen it can have, and so of course that leads to a decline in fish health. Last one, radioactive. So often we're talking about mining here. Of course, nuclear power is another one. There are some natural sources, of course, of things. For example, uranium is rich in certain parts of Saskatchewan. And also, I believe there was a uranium mine near Lake Athabasca, near Fort Chip at one point. So there's always questions as to whether any of the uranium in the lake is natural or whether it was due to the mining. Of course, this is, again, health effects. So a bunch of different types of pollutants, right? So just a little tip for you on the next test. Make sure you know an example of each of these. I'll probably ask, a couple of questions around this kind of thing.
Mm-hmm. Are you gonna, so for those to study, and are you gonna have this on the Moodle or on the lecture thing when you post it?
It will be in the lecture video. If you want, I can always email it to you. Just remind me because I'll forget by the time I get back to my office.
Yeah, I'm almost. Oh yeah, guess what? So on that PowerPoint, I'm actually almost completed the big assignment for the water treatment plant. Yeah, so I'll talk to you about that next week, and we can figure out what we're gonna do. You know what's a cool factor I did not know that I learned? Sure. So I don't know for the one here that did it, but like this, but in Winnipeg. So they actually put fluoride in their water system.
Yeah, so we'll talk about fluoride and then a few other things, certainly in the next couple of units. They don't add it here in Fort McMurray, but they used to. So that's something kind of interesting to discuss. So, or actually probably we'll talk a little bit about fluoride as a part of this topic, but probably not going to get to it today. So one thing that you can see when you take a look at these categories is that at least 3 of these categories you can include sewage or you know, some sort of fecal matter as part of that, right? So just something else to think about. So what happens when we fertilize our water? Just remind you of that word when we're talking about a fertilized water, body of water. The term is eutrophication. Often when the word is used, it's implied that it's human caused. So, you know, we're dumping fertilizer or sewage or something into a water body source, either intentionally or not. But eutrophication is a natural process as well. So I mentioned like Gregoire Lake, like a lot of lakes in this part of Alberta are well fertilized. Probably, you know, if you're from almost anywhere else in Canada, you know that the lakes in this part of Alberta, I hate to say it, but they're kind of swampy. It's true. Well, what does that mean? It just means that naturally they've been fertilized by forest, and, you know, leaves and other particles get in there over the years, and you know, they're not as pristine as maybe lakes that were formed more recently geologically. So, but you know, when we speed these things up, that's where we get the problems like the algal blooms. So yeah, I guess we kind of talked about algal blooms already a little bit and eutrophication, but it's obviously going to lead to a difference. You know, it's going to affect the ecology. So you can see it's talking about how pollution is going to affect the balance, and it's going to generally what happens is you get more smaller fish and less bigger fish, but the opposite can happen again, just depending on the exact balance of the whole lake. I think I mentioned Lake Winnipeg is a good example where the fish are actually getting bigger because they have so much to eat. And Lake Winnipeg is big enough that the algal blooms, they affect the dissolved oxygen a little bit, but not enough to kill the fish. Probably because it's such a large body of water would be my guess, but I don't know enough about Lake Winnipeg to confirm that or not. So one thing you can see that says that fish are a good indicator of water quality. Why would that be?
Because they live in the water they breathe.
For sure, yeah.
Water.
And it just makes sense. It's kind of one of those general things. When you see more biodiversity, usually you're looking at a healthier ecosystem, right? If all the fish are dead, if you only have 1 or 2 species, it's an indication something's not quite right. You have good variety, and it means you've got good water, right?
And some species and their fish species, some fish species are so sensitive to specific type of water.
Yeah. So there's one thing they do sometimes when I think they have to send away a sample. I'm not exactly sure how frequently they do this, but one thing that they do at the wastewater plant is they send away a sample once in a while, and it goes to a lab, and literally they put fish into it. Like I think they're using perch or something, and it's sort of a test to see, you know, are these things surviving or not, right? And you know, like I said, it's not done daily, but it's occasionally. I have to ask them about that. It's kind of an interesting little test because, of course, you're directly seeing, can the fish live in it, even if we know what's going on with all the other water quality parameters. So other things, I think we talked about some of these things already as well. Like a lot of this has to do with biological diversity and health of the fish and whatnot. Question?
Oh well, actually, Blaine, about the field trip, like the finance, I was just taking a look at the calendar.
Yeah.
So actually, April 5th is a holiday. Same for April.
Yeah, I had mentioned that at the beginning. I didn't realize it until this morning, actually.
Like the 1st is a Thursday, and like the 6th is,
yeah, so we're probably going to do the 1st and the 6th, but I still have to get in contact with them, so I'll give you more information as I get it.
Or even like maybe the 7th. You never know. Whatever day it works with.
Yeah, I have to kind of negotiate it with them when they're not busy too, right?
Yeah.
Something else is turbidity as well, and so was hoping to talk about turbidity today, but I'm just not sure if I'm going to get quite to it. But we're going to talk about solids and turbidity, which is actually related to tomorrow's lab. So like I said, I'm hoping I'll get to some of that here in a few minutes. So groundwater, of course, is something that's important, as I mentioned, at least a couple of times, right? And it can get contaminated. Here are some common ways that groundwater gets contaminated, right? So you can see, for example, septic tanks are a good example of where sometimes they are close enough to a water table, they're getting into somebody's well or something like that. But all the usual sources, right, of human activities that are going on are possible to contaminate groundwater.
Blaine, I have a question.
Sure.
Would groundwater be considered uncontaminated?
Well, it really depends. Groundwater, the quality can be actually, in some cases, very pristine. Kind of depends on what is trapping that water. In some cases, groundwater is very pristine, particularly if you have a very sandy soil. The sand actually acts as a natural filter.
Yeah, because we did some sampling last week in that well. I think I told you that, and we collected the water, and the water is actually pretty like clean. I thought it would be like
it can be, yeah. It really depends on what's kind of in the ground. Sometimes it's picking up a lot of dissolved ions. Sometimes it's picking up dissolved gases, particularly if there's a lot of decomposition, organic matter in there. Some groundwater is contaminated by arsenic or other heavy metals that's just naturally in the soil. And it really depends. You probably know that, like I think we mentioned, we talked about well water before. I've seen wells that the water is just amazing. And then other times, it has a little bit of a color to it or a funny taste to it. And just really just depends.
Okay.
What was else I was going to say about groundwater? Yeah, you probably talked this with Neil a little bit. It moves slow. And so I think the big thing to say about groundwater is it does get contaminated. It's not really that easy to deal with it. In some cases, when groundwater is contaminated, it really means they go in there and they dig it all out, with massive loads and dump trucks and things like that. But in most cases, when groundwater gets contaminated, that's kind of it. It's going to take a long, long time before it naturally cleans itself. It's not going to be worth it. It's too expensive to dig it all out. So groundwater protection is something we think about a lot. And so you'll see with gas stations, any newer ones that are built, they're starting to store the gas outside of the ground. All older gas stations have buried tanks. And pretty much it's kind of the rule is that those things leak eventually, no matter what, they will leak. So when a gas station is decommissioned, that's the first thing they do. They dig out the buried tank. Like I said, newer gas stations, they're pretty much all storing the petroleum above ground. So one thing about water sources, and I meant to put this in the last unit, is that water sources have to be protected. And hopefully that's obvious why. Particularly we're drinking water and using it for other sources. And so one way that we protect our water sources is something called this multi-barrier concept. So what that means is that you have multiple layers of protection around your water. And if if one of these things fails, then the water is probably going to be okay. And for example, you can see if you look at this source protection, right? So what does source protection mean? It means that we're not allowing people to dump their waste into the river upstream of where we drink it from. We are, in some cases, for example, some cities have reservoirs, and depending on what's going on with those reservoirs, we don't actually have fences around our reservoirs here in Fort McMurray. Maybe they're not necessary, but I've read in some cities, they actually have fences around their reservoirs because they're trying to keep deer out. You can imagine deer are going there, and if the population is really high, they're pooping in it and they're doing other things in it, and that's not so good. New York City has a very big reservoir. I can't remember what it's called. It's a lake, and it's all fenced off, and that's exactly why. They're just trying to keep the wildlife out of it. The water treatment is part of the system. The chlorination is kind of it is part of the water treatment. but it's kind of mentioned as a separate thing because the chlorine stays in the water as it's being distributed between the water treatment plant and your house. And so it's kind of its own separate thing there. You can see number 4 there is just properly maintained infrastructure, right? Making sure pipes and all those kind of things are, you know, in good shape and not picking up things as they go along. So here is another schematic talking about, you know, the water. You can see on the left there, it's getting treated, stored in a water tank, ends up at the homes and businesses, then goes to a water treatment plant, and then ends up being discharged back to the environment. So these are some processes we're going to talk about in the next few minutes. So something to think about is really we're going to be kind of dividing this into 2 or 3 things, depending on how you look at it. One form of water treatment is for drinking water. And you can imagine that the standards for that are going to be quite high. You know, we don't want to be messing around with human health, making people sick and all that. And so they're actually set by Health Canada, which is one branch of the government in terms of, you know, the people they're looking at health, and they're directly looking at, you know, how these things affect humans, right? The wastewater treatment, it turns out, is actually governed by Environment Canada, because of course we are discharging the wastewater into the environment. Indirectly, it's actually Alberta Environment, or is it Alberta Environment or Environment Alberta? I can never remember. They're the ones that locally manage wastewater disposal in Alberta, but they are, you know, directly governed by Environment Canada as well. Okay, so yeah, and then local and provincial agencies can also have regulations, right? So sometimes there's other things going on in terms of, you know, we may have things that are different in Alberta versus BC or Saskatchewan. So water quality standards. We're kind of looking at 3 things. Sometimes people consider 4 things. They, you know, there's physical versus chemical, or sometimes separate out a little bit differently. But we're looking at the microbiology, the chemical, and the aesthetic. By aesthetic, we mean, does it look and smell nice, right? So these are some of the things that I want to talk about today, at least a little bit. And all of these standards for drinking water come from that document that you were directed to online in Lab 3 called the Guidelines for Canadian Drinking Water. And this is a document that is updated as information comes along. So every time I've checked it, you know, it seems to me there's a new date on it. So I'm guessing they update it at least a few times a year as they get new information. And you can imagine, you know, with research, there's new information that kind of comes along, you know, occasionally here and there. And this is developed by a whole bunch of agencies across Canada. And I think ultimately it does fall under Health Canada in there. So 1968, well, there we go. Yeah, there's a date for you. Wastewater conditions, you can see there's actually a whole bunch of different, like I said, different organizations under this. Environment Canada and the Fisheries Act is a big thing. I don't have a date for that on you, but these things have not always been necessarily mandated, right? It's kind of strange to think that before 1968, what were we doing with our water? But it takes time for these things to get through the systems as governments get organized. So some numbers I want to introduce you to are something called the maximum acceptable concentrations. It turns out there's a whole bunch of acronyms for this exact thing. For some reason in the States, they call them maximum containment levels, so MCLs. In Europe, they use MAC as well, but it actually, the acronym stands for something different, maximum admissible concentration. Those are all the same things. So what this means is that this is the maximum number, the maximum concentration of some sort of contaminant that you would have in the system. So everything in the Canadian drinking water guidelines is going to have a number. So, you know, if you look up arsenic, it'll say this is the maximum amount of arsenic in parts per million you're allowed to have in the water for to be acceptable for drinking, and so on. Some things, if you look up, just trying to think what I was looking up recently, was it copper or was it iron? One of those doesn't have an MAC. I think there's a note that says no adverse health effects known. I can't remember if it was copper or iron. Maybe it was iron. Although it may affect the taste. Iron's actually good for you, right? Sometimes they talk about these sort of goals, and so you can see MCLG. meaning that you know, the MCL is the legally enforceable standard, but they're hoping that municipalities will try to meet these goals as well. So, oh, wrong way. So what are they looking at when they're looking at MACs? All the usual things, right? Health effects, toxicity. They're looking at things like, you know, if you look at, say, a campground versus your home, there's actually slightly different standards. Campgrounds are allowed to have, their water doesn't have to be as pristine because it's assumed that you're not drinking it 365 days a year. You're probably staying there for a few days or a week kind of thing. And so there are slightly different standards based on the actual use, right? And obviously, you know, all the other usual things, but a lot of it is around human health, of course. I thought I had some examples here, or maybe I'm going to go through the examples here shortly. Let me just see where we are with time. So I want to talk a little bit about each of these physical properties. I'm just going to talk about solids for a minute here. You can see all that stuff on the left, the chemical characteristics. We've kind of covered all that stuff in topic 2 in this course. We were talking about dissolved ions, things like hardness, pH, alkalinity, and so on. But a big part of measuring water is also looking at the amount of solids. So I'm just going to spend maybe 2 minutes on that to finish up class, and just as an introduction, so you guys are ready for tomorrow's lab. So if you take a look, there's lots of ways to define solids, and this is what you're going to do. You're going to measure all of these tomorrow, except for the volatile solids. We don't have a furnace that goes up to 550 degrees, but we can do all the other tests. So if you take a look at these, they all have slightly different definitions. So total solids basically means what happens when you dry the water up, what are you left with? That's the total solids. So it's a very simple test, right? You're going to basically get a little dish. It's kind of a little aluminum dish. You can imagine it's I can't remember what volume it holds. You put your water in there, and then we put it in, so you weigh the dish, by the way, before you put anything in it. And then we put water in. I think you're going to use 50 mils or something like that. And we're going to dry it out in the oven, and then you weigh it afterwards. And so you can imagine some of the water, like the salt water, is going to have a lot of particles in it, the tap water a lot less. And that's how you're going to determine the total solids. Settlable solids is really just that. What settles out over an hour? So we have these things called Imhoff cones, and literally it's just a big cone like this. You put the water in, you let it sit for an hour, and you can see if, you know, do we have any debris that gets collected in the bottom after the hour. Total dissolved solids and total suspended solids are slightly different. So total suspended solids, you can see the key word is what is caught on a filter. So this is looking at basically larger solids. So you can imagine anything that catches on a filter, bacteria probably too small, but anything larger than a bacterium would be caught in that filter. So large clay particles, sometimes organic things, cellulose, pretty much anything you can imagine. So different ways to look at the solids. So tomorrow you're going to get a chance to basically do these tests in the lab. They're relatively straightforward tests. Like I said, we're measuring and drying things out and measuring again, and the whole lab, everything's being done in triplicate. And so I think Fahad had pointed out that this was a 2-week lab. And so next week, you guys are going to have another Excel tutorial where you're going to crunch the data. Everything in triplicate, hopefully that means you're going to get some good numbers. I think the way tomorrow is going to do it for you is every group is going to be assigned a different water sample. So one group will do the tap water, one group will do the groundwater, and so on. And then we'll pool all our data and use the second week to analyze it. There are some formulas that go with it. Probably don't need to worry about them so much today, but when you do the lab, and we'll review these formulas on Monday, and I'll show you some sample calculations on them. So the one other thing I just want to point out today is turbidity. And this is the last test you're going to do tomorrow. So turbidity is really, in a sense, how murky something is, right? So if water is turbid, it means you can't see through it very well. And we're going to use an instrument called a turbidometer. That is not the one we're using, but that's a sample turbidometer. And in some ways, it's similar to spectroscopy, where you have a sample and it's going to look to see how much light passes through that sample. And so this instrument that we have in the lab, there's a calibration method to it, and Tamara is going to go through that with you guys tomorrow. And the values are going to come out in NTUs, and I can never remember what the N stands for. It's like neptrophlowmetric or something like that. But the TU stands for turbidity unit. And so you can see this number here. It says drinking water should be less than 0.5, and they're apparently revising this value to 0.1 in Alberta for drinking water. So whoever does a tap water tomorrow, you can tell me what our tap water comes out as. That would be interesting. But anything more than that, you can't see it with your eyes unless it's about a 10, and then you can actually start to see some of the samples in there. Okay, that's it for today. So good luck with tomorrow's lab, and hopefully that goes well, and we'll get a chance to kind of revisit these parameters on Monday.
Yeah, thank you, Blaine. Hopefully, we'll get that trip finalized.
Yeah, so I'm hoping to give them a call today or tomorrow again, and hopefully I have some details sorted out.
Yeah.
All right. Thanks, Blaine.
All right, thanks. Have a good day.